Hello again, my dear students, and welcome to the second part with our p-n junction semiconductor device. In the first part, we have studied together what we call the p-n junction performance under thermodynamic equilibrium, whenever there is no applied voltage to the junction. Today, we are going to continue with our part 2. In part 2, we are going to demonstrate the same p-n junction, but under no thermodynamic condition. I mean, whenever an external voltage is applied. Herein, we have two main cases, what we call the forward bias and what we call the reverse bias, depending on the polarity of the externally added voltage. Now, please let me share my presentation slides and continue with you the second part with our p-n junctions. Perfect. Okay, so I think now you can see my presentation slides for this lecture number 2, p-n junction, and I can now start operating my laser pointer as well. Perfect. So, if you remember, in the previous part, we have discussed the combination of the n-doped region and the p-doped region in what's called the p-n junction. First, we have prove together that the Fermi level as the reference for thermodynamic equilibrium condition should be totally flat whenever there is no applied voltage to the device. Accordingly, the p-n junction energy band diagram can be categorized into 3 regions: a purely n-type region on the extreme left, a purely p-type region, in the extreme left, a purely n-type region in the extreme right, and a depletion region. The depletion region, by definition, is the region where there is no free carriers exist, because basically any electron in this drift area will be automatically drift to the right, and any hole in this drift area will be automatically drift to the left. That's why in this region we don't have any free carriers. And we also have proven that the overall current flowing inside the device at this stage is equal to 0, because the drift current will be cancelled by correspondingly the same equal in magnitude but opposite in direction diffusion current. So the overall current flowing in the device is equal to 0, and this is actually makes sense because you don't have any applied electrical field or applied potential. Okay, then we have also plot together what's called the carrier concentration inside the material, where we have a p-doped region. So as you can see, holes is a majority and electrons are the minority. Similarly, but in the reverse direction, for the other region, we have a majority of electrons and a minority of holes. And as you can see, we have fixed a terminology where we call the big upper letter indicates the carrier, either the electrons or holes, and the subscript letter indicates the region, and the node indicates the thermodynamic equilibrium. So for the P region, the holes will be called PP node, where P, the first P indicates the hole, the second subscript P indicates the region, which is a p-type region, and the node indicates the thermodynamic equilibrium. Similarly, you can also terminate all the other 3 terms with the same terminology or procedure. And herein we have reached, using this equation, this equality equation, we have reached an expression for what we call the built-in potential inside the junction. It's a built-in because this is a natural potential created due to merging the P region with an N region, and we have found that this built-in potential is equals to, or it's proportional to, the temperature of the material, the doping concentration in A and in D, and of course the material itself, which is the intrinsic concentration, or NR. Then we have discussed together the equality of a charge, and we reach these two important equations regarding the depletion region, where we define the depletion region to two separated regions. The first is in the N region, which we call it Xn, and the second in the P region, which we call it Xp. Again, the term node is used to indicate thermodynamic equilibrium, and logically, the W, which is the total width of the depletion region, is the summation of Xn and Xp. And due to that equality in charge movement, we say that Xn times Nd equals to Xp times Na. And finally, we have these three major equations determining W, Xn, and Xp. And as I mentioned in the end of the lecture, I told you that in the final exam, maybe in the class test, I will only give you one of these three equations, and you can automatically expect the other two using this sign, using these two equations. So this typically what we did in part number 1. Now in part number 2, we will describe together what if this BN junction is connected to an external potential source, an external voltage, an external battery. What will happen to the energy band diagram, the carrier concentration, how current will move, if there are current or not? All these questions we are going to answer during this lecture. Okay, so now let me first start with you the thermodynamic energy band diagram for a PN junction. If you remember, we have an horizontal line to represent the Fermi Dirac. Then we have a p-type material. So now this is EV and this is EC. And we have correspondingly an n-type region like this. Okay, perfect. This is an energy band diagram for a thermodynamically equilibrium PN junction. Now we have what we call the internal drift. This is the building potential. The sign for this building potential is simply that we have a tilting in the energy band diagram, as you can see in this region, and as you can see also in this region. Perfect. So can we determine or estimate the direction of this potential? We have actually two ways, one conceptual and one graphical or mathematical. The conceptual one is very easy. So assume that you have an electron here. So based on the drift theory, this electron will drift in this direction. That means that you have a positive terminal of your potential in this direction, because electron is a negative particle and the electron is attracted to the positive terminal. Similarly, if you have hole here, hole will drift upward as you know, and that means that you have a negative potential terminal here. So as if we are connecting this semiconductor with a battery in this connection. So of course this is a virtual battery, because we are not connecting our device with anything. This is under thermodynamic equilibrium, as you can see, but virtual, as if we are connecting our device with a battery in this polarity. So electrons are drifted to the right and holes are drifted to the left. This is what we can estimate. Now, this is the first way where you can estimate your potential. There is also another way. If you remember your material course, when we have said that the potential V is negatively proportional to the energy, if you remember, this was a very famous question in your material module whenever I gave to you an energy band diagram and I told you please sketch the potential. So what you are going to do is just to multiply this curve by negative. So if you are going to, if you make it like this, you will find something like that. So this curve is typically the negative of this curve. As you can see, higher voltage is here, lower voltage is here, which is typically the same like the battery we have estimated. So either by doing it like this or like that, both you will have the same conclusion, that the higher potential is to the right and the lower potential is to the left. This is the conclusion. Now, as I mentioned, this is a building potential. This is a virtual battery. Now, what if we connect our device with a real external bias source? What if we go to this two terminal? Let me make it with another color. So what if we go to this two terminal of the device and start to connect them with a real battery? This is the p-type region and this is the n-type region. Okay, so basically here you have two probabilities. Either to connect the p-type region with a negative terminal of the battery and the n-type region with a positive terminal of the battery, which is typically the same polarity like the building potential. And we will call this the reverse bias of a p-n junction, and we will know why we call it the reverse bias. Or to connect the positive terminal to the p side and the negative terminal to the n side, which is against or the counter direction, the counter polarity of the building potential, and we will call this as the forward potential or the forward bias p-n. So these are the main two possibilities we have in order to connect our p-n junction with an external biasing source. Okay, perfect. Let's now start to discuss our energy band diagram from another point of view. Okay, again, I'm still under thermodynamic equilibrium. This is the p side, and this is the n side. Okay, so now in this energy band diagram, we have stated that the overall flowing current, the net current, is equal to 0, because you have a drift current and diffusion current against each other, and the net is equal to 0. We already have discussed this in part number 1. But let's discuss together what is the possibility to have current. Or in other words, here we have 3 regions. The middle one is the depletion region. Okay, let's skip it. This is the p region, and this is the n region. In the p region, you have majority of holes and a minority of electrons. And vice versa is in the n region, you have a majority of electrons and a minority of holes. And as you know, current is the flow of a charge. So in order to generate current in this device, you should rely on, you should act on the majorities. Minorities are very low, so whenever minority create current, the current will be very, very small. But in order to have a significant current, you have to push, to motivate the majorities. That means that you need the electrons here, which is the majority, to move in this direction. And typically, the holes here to move in this direction. But the question is this possible given this condition? I mean, now you have an electron here, which is a majority. Is this electron capable to move to the other side to create current? The answer is no. Why? Because when electron starts to move to the left side, the electron will find what we call a barrier. Because this potential energy is higher than this potential energy. So naturally, electron will not be able to move from the right to the left due to this barrier. Similarly, can be seen from the whole perspective, from the whole point of view, when you go to this side. Here in hole, see a barrier, because if you remember, the energy of the hole increased downwards. So this potential energy is higher than this. Accordingly, naturally, hole will not be able to move from the right, from the left to the right. It needs energy, and this needs energy. So the built-in potential is considered as a barrier from the majority carrier point of view. From the majority carrier point of view, this is a barrier. Accordingly, you have to get rid, you have to damage this barrier first in order to create electrical current. Otherwise, you will not have an electrical current. Again, or you will not have an electrical current due to majorities, to be 100% correct. So, if this building potential have this polarity, if you remember, this is connected to the positive, so electrons comes here, and this is connected to the negative, so hole comes here, this, if you remember. So in order, so this is the negative and this is the positive. So in order to make a forward bias p-n junction, I mean, in order to make a huge current flowing in the p-n junction due to the majority hole, you have to get rid of this barrier. And the only typical way is to insert a potential which has the opposite polarity. This is 100% makes sense. Why? Let's see. This black potential is a potential with a polarity against the building potential. As you can see, this is the positive and this is the negative. Now, if you connect this potential like this, what will happen? Let's make it in a very conceptual manner. Here, this is the positive terminal. This is positive. Electron is negative. So now electron has energy, has an attraction force to pass the barrier. But without connecting this black potential, the electron will not have, or will not have this energy to pass the barrier. Similarly for holes, now this is negative, connected here negative. So now hole is attracted and can pass the barrier. So whenever you connect a potential in the anti-direction of the building potential, you are motivating majority carriers to move from left to right and from right to left, and accordingly you have a current. So that's why we call this the forward bias. And of course, the other is a reverse bias. Now, let's discuss together how we can plot an energy band diagram for a forward biased p-n junction and then go to the reverse biased p-n junction. So the first step is to try together to plot the energy band diagram when you put this black forward bias, or when you put a reverse bias, which is the same direction of the building potential. Okay, perfect. So let's again start with the energy band diagram under thermodynamic equilibrium. But in this case, I will try to divide the page into 3 regions. So this is the first one. And this is the energy band diagram under thermodynamic equilibrium. And herein is the depletion region. Electrons are moving in this direction, and holes are moving in this direction. So this is the positive terminal of the battery, and this is the negative terminal of the of this battery. Again, this is a building potential VP, or we can call it V node, based on our terminology. Okay, perfect. So this is the standard case. Now you go to your semiconductor material here. So here, your semiconductor material or your p-n junction. Your p-n junction is not connected to any potential. Here, you go to the p-n junction and you connect it like this. As you can see, this is the anti-direction for the building potential. Okay, so now we connect our battery, our p-n junction to this polarity. So as you can see, now the positive terminal is to the left. That means you are pushing electrons. As I mentioned, and maybe we already demonstrated this in the previous slide, whenever you add a potential, which is against the building potential, now you have 2 opposite potentials. And the one who will win this is the larger one. So whenever you add a building potential, whenever you have add a forward potential, you have to ask yourself a very important question. Is this forward potential is greater than or smaller than the building potential? This will make a big difference in our calculation. So here you have to check the values here, because if this voltage, which is the building potential, is greater than the forward voltage, this barrier will still exist. However, when the forward potential, the external forward potential, is greater than this potential, the building potential, then this barrier will disappear. So the summation of the potential here, in this case, is as follows. So the overall voltage applied in the case of a forward bias is V node minus Vf. Of course, this will be turned to be negative whenever Vf is greater than V node, or positive if V node is greater than Vf. Accordingly, we can plot 2 energy band diagrams for this forward condition. The first one is when V node is still greater than Vf. So what will happen is still V node is greater, but this barrier, which is V node, will be reduced to be V node minus Vf. So your energy band diagram will look like this. As you can see, electrons here still can see a barrier, but the value of this barrier is smaller, is V node minus Vf. As if, my dear students, we pick up this N region and we slightly move it upward. Accordingly, in this case, you will find what's called a splitted energy band. If you remember, my dear students, I told you, whenever the energy band diagram is horizontal, then this is a sign for thermodynamic equilibrium. No external potential is applied. However, when there is a potential is applied, then we should expect a split energy band gap. And this is the case. The energy band gap will start to split to keep this n-type, sorry, p-type, and to keep this n-type. And now the barrier is left like this. But what if the V forward starts to be greater than V naught? Then now no barrier will exist, and the energy bandogram will look like this. So as you can see, the barrier seen by the electron, which is the majority carriers in the type, starts to be turned to adrift, as you can see here. So electrons move smoothly from the right-hand side to the left-hand side, and you have a huge amount of electrons. So this is the two cases. Now, let's go to the second case, which is the reverse bias. I mean, your p-n junction is connected in a polarity which is similar to the building potential. So you are increasing the building potential. That's why in this case the voltage will be V node plus VR, where VR is the reverse bias. And accordingly, you should expect a higher barrier, which is V node plus VR, as you can see. So this is V node plus VR, and this is the overall energy bandogram. Again, here the energy level is splitted and not a continuous energy level. So these are the different conditions for the energy bandogram. As you can see, you can adjust the height of your barrier based on your forward or reverse connection. Whenever you have a forward connection, your barrier starts to be reduced till it vanishes. Whenever you have a reverse connection, your barrier starts to increase. The question is, how shall the carrier concentration change while changing the energy bandogram, or while changing the binding condition? We have already plotted the carrier concentration for electrons and holes whenever we are under thermodynamic equilibrium, which is this case. What if we have a forward case or we have a reverse case? What will happen, my dear? Okay, let's do it step by step. Okay. Again, I'm going to divide the page into three portions. First, we have thermodynamic equilibrium. As you can see, this is a thermodynamic. In this case, if you remember, my dear students, our carrier concentration looks like this. So this is PP node, the majority holds, and this is PN node, the minority of the holes in the N region, and this is NN node, and this is NP node, as you remember. Now, if we apply a forward bias, let me say that we have V node, it's still smaller, is still greater than VF. So what will happen to the energy bandogram is that the barrier will be somehow reduced. This is V node minus VF. Okay, what will happen to the carrier concentration? This is the question. Now, if you remember, my dear students, let me make it in a bigger page. Whenever you have a forward bias, then your barrier is lower. So this is electrons, and this is holes. These, don't forget that these are the majority cases. And of course, the minority are here. So we have here some few electrons, and we have here some few holes. Okay. Now the barrier has been reduced. So maybe, of course, you are inserting here a positive voltage here, and this is a negative voltage because this is a forward bias. So maybe some electrons, due to this attraction force, can move in this direction. And maybe some holes, due to the attraction force, can move in this direction. So carriers will start to move from the majority to the minority. However, there is still a little barrier, which is V node minus Vf. So the flow of the electrons and the holes will not be significant, but there is a weak flow of electrons, let me say so. Okay, so if we would like to reflect this on the energy band diagram, how we can make it? So this is the energy band diagram under thermodynamic equilibrium. How this, sorry, this is not the energy band diagram. This is the carrier concentration at thermodynamic equilibrium. How this carrier concentration will be affected by this movement. Okay, let's start, for example, with electrons. So this curve is with electrons. So this is N node, and this is NP node. This is the majority electrons, and this is the minority electrons. When you start to flow from the majority to the minority, what you should expect? Basically, it's very makes sense. What will happen that this majority will be somehow reduced, and this minority will somehow increase. This is very logical. But which of these two motions, which is of these two variations, is more detectable? Usually, I use this example. If you have two friends, one is very rich and one is very poor. The rich man has $1 billion in his bank account, while the poor man has maybe 10 pounds or $10 in his bank account. Now, the rich man starts to give the poor man some money. For example, he will give him $1,000. So his bank account is reduced by 1,000, and the poor man's bank account is increased by 1,000. Which of these one will observe a change in his bank account? Of course, the poor man. The rich man will have 1 billion minus 1,000, which is almost 12 billion. Nothing has been changed. But the poor man will have $10 plus 1,000, which is $1,010. So whenever we start to plot the carrier concentration, we will not see a significant reduction here, because this is a rich man, this is the majority. However, we will examine, or we will observe, a significant increase in the minority. So the new line will look like that. As you can see, the rich man, the majority, is not affected. However, the minority increase, as you can see in this curve. Similarly, for the holes, this is a rich man with holes, and this is a poor man with holes. So your curve will look like this. So this is the variation in holes and in electrons whenever the voltage is passed. Of course, while you increase the VF more and more, this dotted curve will go upward more and more because you are pushing more electrons from right to left and more holes from left to right. This is the case where we have the majority and the minority concentration due to the forward bias. So let's go to the second one, which is when you have a reverse bias applied to your p-n junction. So whenever you have a reverse bias, you should expect that your barrier will increase. So this barrier now is equals to V node plus VR. Again, let's start with this default curve for electrons and holes. Now, whenever you have applied this reverse bias, it's now impossible for the majority carriers or the majority holes to move, because basically you increase the height of your barrier. So no electrons will move from right to left, and no holes will move from left to right. Does this mean that we don't have current? You can say yes. We don't have current due to majority carriers. But please don't forget that you have a minority carriers. You have here minority carriers, whole electrons, and you have here minority holes. And by increasing this barrier from the majority perspective, or from the majority point of view, you are increasing the drift from the minority point of view. So maybe some minority carriers will move this in this direction. And similarly here. So you will have what's called a current due to minority carriers, which is in your previous study, you called the reverse current for a current. So in the reverse process, we still have current, but this current is very, very small with respect to the forward current. Because in the forward current, the current is conducted due to majority, while in the reverse current, the current is conducted due to minority carriers, as you can see. How this will affect the energy, the carrier concentration? Now, life is reversed. The poor man is now the one who is giving transfer to the rich man. So, the one who has 10 pounds in his bank account will pay, for example, 5 pounds or $5 to the rich man. So, he will be strongly affected. He loses 50% of his saving. However, the rich man who has already $1 billion in his bank account will have 1 billion plus $5, which is 1 billion. Accordingly, what you will see is as follows. You will find something like that. And similarly here. The rich man is not affected, but the minority carriers is reduced here and here due to the reverse current. My plotting is just too bad, so let me go now to the presentation slide where you will find better plots, I think. So this is the presentation slide. Okay, so first, this is the three conditions. First, this is, okay, so as you can see, here we have the three scenarios. This is the normal thermodynamic voltage where there is no voltage applied to the semiconductor material and to the PN junction, and then you only have the building potential. If you add voltage, which is, again, this is the energy diagram. If you add voltage, which is in the forward bias, but as you can see, this is still smaller than the building potential, then this is the potential, and this is the energy diagram. And of course, this is the other condition. When you have a reverse bias, then the barrier increase, and this is the energy diagram. So these are the three typical conditions. And accordingly, this is the forward bias case when the minority carriers increase. As you can see, we remove the dot from here to indicate that this is not under thermodynamic equilibrium. So the carriers increase here and here, and then this is due to the forward current, or the current due to the forward, the current due to the majority carriers. By the way, this mathematical steps is not required from you. You can find it in the scripts for your information. However, you are not obligated to remember these equations, and whenever we need any equation, it will be given in the formulation. So you don't need to memorize this equation. Okay, so this is a majority case, and inversely, this is a minority case when the this is a reverse case when the minority starts to decrease, as we described, when the poor man starts to give money to the rich man. So this is the two cases. Accordingly, we can reach what we call the general IV characteristics for a dot. Within this IV characteristics, again, the mathematical derivation is not required. This is a very famous equation for the IV characteristic curve, where I know we call it the saturation current, and this is typically the formula for the current. It depends on the diffusion coefficient, the lengths, and the concentrations. A is the area and Q is the charge. And here we have E power minus QV over KT minus 1. I believe that most of you already remember this equation from your year 1 electronics course. So this is the general IV curve. You have here 4 regions of operation. First, I can tell you, please, my dear student, where is the thermodynamic equilibrium in this curve? Please indicate the thermodynamic equilibrium in this curve. So you can say easily that thermodynamic equilibrium is the origin point. So this origin point, whenever the voltage is 0 and the current is 0, is the thermodynamic equilibrium condition. You can find it here. No voltage is applied, the voltage is equal to 0, and then the current is equal to 0. Second, we have the reverse condition. Whenever the voltage is negative, reverse, then you have a very, very small current flowing in the PN junction, which is a reverse current due to the minority carriers. Then we go to the forward condition. In the forward condition, we have 2 cases. When V is smaller than V naught, which is this case, so you have current, but the current is very, very small, because you still have a barrier, like this case, you still have a barrier, as you can see. However, when the voltage applied is greater than V naught, the current starts to increase exponentially, currents increase in a very significant manner, and of course, this current is due to the majority carriers. So this is generally the IV characteristic curve for a dot. I believe you already know this IV characteristic curve from your previous courses. However, we just describe it from a semiconductor perspective. Now, let's go to this case, which also I think you already heard about it before, which called the breakdown potential. I mean, whenever you insert a very large breakdown voltage, a very large reverse voltage to the light, what will happen? This is called a breakdown. By the way, breakdown voltage is not only in diodes, it's maybe in most of the semiconductor devices. And we will going to demonstrate it in MOSFETs and in BGTs as well. Okay, but now what we are going to answer, what is the purpose? What is the reason for a breakdown? Why our device breakdown? Actually, we have two reasons for the breakdown. The first one is what's called the Zener breakdown. And of course, you know it from your background about Zener diodes. What we are going to demonstrate is just that semiconductor concept of this Zener breakdown. Herein, as you can see, you are increasing the breakdown voltage so that the valency band for the p-type is horizontally aligned with the conduction band in the n-type. As you can see, we increase significantly the reverse. So this starts to go down more and more. If you can remember it from this, as you can see, this, and whenever you increase the reverse bias, this region and region is going downward. So it's going downward so that the conduction, the valency of the p-type is horizontally aligned with the conduction of the n-type. Where is the issue here? To have the valency of the p-type horizontally aligned with the conduction of the n-type. The valency of the p-type is a region where we have a huge amount of electrons, and the conduction of the n-type is an empty or partially empty state. So now electrons, due to this high electrical field, high energy, electrons can tunnel the gap and can go from this stack of electrons, which is the valency band of the p-type, to this empty state, which is a conduction band of the n-type. And this is what we call the tunneling current. By the way, this tunneling current is very, very interesting in semiconductors. Maybe by the end of the semester, we will have some demonstrative lecture about new technology. And here we will study what's called the TFET, or the tunneling field effect transistors. This is one of the promising transistors in the market, and its carrier transport methodology is based on the tunneling current, which is the same like in the Zener diodes. Another reason for what we call breakdown is what's called the avalanche breakdown. Of course, whenever you increase the V reverse, that means that you have higher electrical field in the depression region. So higher electrical field, if you remember, electrical field is the mobility times the velocity. The mobility is constant. So electrical field increase means velocity increase. Electrical field and velocity, I mean drift velocity, of course, are directly proportional. That means that whenever you increase the electrical field, the carriers, which is a minority carrier, because this is a reverse current, the carriers will move in a very high speed. And as the carrier is moving in a very high speed, that means that it has higher kinetic energy, because kinetic energy is proportional to speed. And thus, this carrier can collide with another electron which is already bounded and broke its bond to create another electron. So you have one electron moving, then this electron moving is moving in a very high speed. It collides with a static electron, turn it to be free electrons. So after the collision, you have two free electrons instead of one. And as you know, current is directly proportional to the number of carriers. So whenever you increase the number of carriers, you increase the current. And in this case, due to this mutation of electrons, you can say that you will have a very huge current, which is the breakdown current, or what we call the avalanche breakdown. So this is the other reason to have a breakdown. Finally, if you remember, my dear students, we have discussed together what's called the capacitance effect of the p-n junction. If you remember in this slide, yes, I told you that this in-between region is a depletion region. So it's depleted from free carriers, or it can be treated as an insulator. Accordingly, we have two conductors, or between quotations, semiconductors loop, and in between we have an insulator, which is typically a capacitance effect. So here we have what's called the associated capacitance with a p-n junction. Capacitance, if you remember from your physics classes, capacitance equals to epsilon, where epsilon is the permittivity of the material, times A, which is the area, over W, which is the length of or the width of the electrical material, which is, in our case, of course, the depletion region. We already have an equation for the depletion region, this is W. Maybe in this equation, I should terminate it as W node, not W, because this is a thermodynamic, this is a depletion width at thermodynamic equilibrium. But you can say that it's very easy. Whenever we have a forward bias, what we are going to do is that we will replace V by V node minus, or we will replace, sorry, V node by V node minus VF. Whenever we have a reverse current, we will replace V by, or V node by V node plus VR. So herein, the capacitance will vary based on the condition. Let me see this. So in the reverse case, your capacitance will be V node, here, this one, yeah, V node plus VR, which is basically in the W equation, you replace V node by V node plus VR. And of course, in the reverse, in the forward region, you will replace this V node by V node minus VF. But a very important question comes now. What if you apply forward voltage with value greater than V node? In this case, the term V node minus VF will turn to have a negative sign. And as you can see in the W equation, this equation is under root. So if you have a negative sign under root, this is imaginary. And of course, it doesn't make sense to have a W imaginary because W is a distance. That's main, or that's the answer is very easy. Whenever V node is smaller than VF, we don't have a depletion region. Because in this case, the barrier will tend to be zero. And this barrier, if you remember, will turn to be a drift. So in the forward condition, the capacitance effect can be easily neglected. We don't have a capacitance, except of course for the region from 0 to V node as a forward bias. However, the capacitance effect is significant in the reverse condition. That's why in this equation, I substitute with the reverse condition of the forward, because this is the condition where the capacitance is significant. This is the termination, my dear student, for this lecture, lecture number 2, or chapter number 2, under the title p-n junction. We have studied in this lecture the two cases of a thermodynamic material, the two cases of a p-n junction, including what we call the thermodynamic material, the p-n junction under thermodynamic and the p-n junction without thermodynamic or under external bias. Now, in the next chapter, inshallah, we are going to go to the most famous device in the semiconductor industry, which is the metal oxide semiconductor field effect transistor, or the MOSFET. Most probably, we are going to demonstrate something like 2 weeks in this lecture. However, maybe we will have one additional introduction week before going to this lecture, where we are going to deal with what's called the metal oxide junctions. This is somehow interesting to deal with the metal oxide junctions and the metal semiconductor junctions, and introduce what we call the ohmic contact and the barrier, or the Shockley barrier contact. This must probably be the next chapter, inshallah. Thank you very much, and let me see you, inshallah, in next week. Thank you, and bye-bye.